And so now we move to Alex Vikman.
Okay, doesn't matter. Okay, so hello everyone, and thanks a lot to, first of all, Andrei Barvinsky and the whole team from Lebedev for organizing this very nice workshop. Also, my friends from INR deserve this many thanks in these hard times. So I'm going to tell you about this global dynamics for Newton and Planck. Okay. Which sounds a bit unusual, but you will see that it's actually more or less standard, but kind of funny. Okay, so most of my presentation will be based actually on this paper, which we just recently published with my student Pavel Jerushek, with Masahide Yamaguchi and his student Keiga Shimada from Tokyo Institute of Technology. And so if you want to know much more actually details, look at this paper. Okay, as I'm not sure we will be on time, but I will try to do all my best. So I want to make the whole message just immediately in words so that you would know what to take home. So first of all, there are local general covariant field theories where the dynamical degrees of freedom are actually global. Okay, for example, they can be given by integrals of a whole Cauchy hypersurface. So actually, this construction looks like a cover-up of the usual, if you want, high school mechanics. But these are normal field series with local, manifestly local actions. So these global degrees of freedom can actually mimic free parameters or fundamental constants. So if you want, it's the simplest paradigm how fundamental constants or coupling constants can change or can be dynamical variables. So actually, we can promote cosmological constant, G Newton, and even, surprisingly, H bar to be such global dynamical degrees of freedom. And because they're real dynamical degrees of freedom, so now they're actually subject to quantum fluctuations themselves. So as you may think, this H bar fluctuating, that sounds a bit unusual and a bit crazy, but that's in some effective sense, you will see what it means. So, but basically for all purposes that will be fluctuating. As I said, they are subject to quantum fluctuations. The key point of quantum fluctuations are uncertainty relations, right? Especially if you don't know how to properly quantize everything there, then you can at least use one direct consequence of whatever quantization, if it is a canonical one or equivalent to a canonical one, namely that there is an uncertainty relation for canonically conjugated quantities. So, of course, here you should follow correspondence principles. So you should believe in matching, like mapping Poisson brackets into commutators. So the point is uncertainty relation for global degrees of freedom, for example, for lambda, can be actually the way to avoid classical end of time singularities in general relativity. Why so? Because as we know, these singularities are global, right? So it doesn't happen at one point in space. It's when the whole space enters the end, if you want. So was our Big Bang. Well, naively, if we extrapolate the hot plasma solution back in time, so there could be a lot of solutions with such situation. And also inside of a black hole, normal singularity is actually really end of time singularity, or what is called space-like singularity. So the point is, if you have a global degree of freedom which cares about the whole Cauchy hypersurface, it can preclude you from really entering into such a singularity. Another thing is what is kind of funny, that even though this construction looks like very exotic, at least I would say, one can really modify this setup in such a way, even though it was normal field theory and even kind of very simple, I would even say simplest field theory, one can actually modify it in such a way so that it looks more familiar or closer to normal particle physics setup. So namely, all these global degrees of freedom can be promoted to be, so to say, frozen axions. So they really look like almost normal axions. So only need what you need to do is to somehow manage to kill kinetic term for your corresponding, let's say, Young-Mills or even maybe QCD action. So here the point is that surprisingly, we talk usually about cosmology and how everything happens, but we have in our world a theory, namely QCD, which is confining, which is actually in IR has a vacuum. The vacuum is a global concept. It's one for the whole universe, if you want. And actually, this vacuum is strongly coupled in large distances, or basically for all distances which we care about in cosmology. So in some sense, it's kind of naive to think, but one can do it and assume that, okay, as there are no separated gluons propagating, just kill kinetic term, because if you don't kill kinetic terms, there will be still propagation. So if you kill kinetic terms, then all these axions become frozen axions, and they can model such global degrees of freedom. Okay, and then the origin of the values of these global degrees of freedom, or if you want to follow our constants of nature, so to say, could be, in that case, in quantum cosmology, because that's the moment when the universe can appear, can disappear, or whatever. And if you want, the current values would be, in that case, just remnants of the Big Bang. So that's the simplest ideal landscape for very poor people. So without using a lot of scalar fields, 10 power 500 compactifications. So here formally you can screen over all possible values of this constants. So that's basically the message to take home. Maybe it's a bit longer than I wanted because it's 6 points, but nevertheless, now you know what I'm going to talk about. Good. So first of all, let me remind you what a strange theory do we have. So if you just assume normal general relativity, it has two, if you want, coupling constants. They're both dimensionful, and surprisingly, they're both kind of smallish, but have inverse dimensions. And importantly, the product, if you of course use h bar equal 1 and speed of light equal 1, in that case, the product is 10 minus 122. And actually, not only that we don't know how to calculate, let's say lambda, but we also don't know how to make sense out of this number. Where can it come from? And that gives you an enigma of gravity. And basically, every time you say which mechanism is behind lambda, you could equally say, using this very nice dimensionless relation, what is actually the mechanism behind G Newton. Okay, so now let me tell you, first of all, as a kind of introduction, so at least then you would know everything. So after that, I will be free because most of the important steps are done for me by other people. Let me introduce the first global dynamical degree of freedom, which is the simplest one. So namely, let's take cosmological constant. And if you want, this is my first way to lose the trace, okay? By that, I mean to lose the trace of Einstein equations. So namely, let's write traceless Einstein equations, okay? Here, for simplicity, 8 pi G Newton is 1. So instead of normal Einstein equations, which I just, which you can see here, I hope, by the way, you can see, because in one of my talks, I was talking about all that in front of my first slide. I hope the slides are changing. Are they? David?
Yes, that's okay. That's okay.
Good, good. So if we take these normal Einstein equations, we can now do something really dramatic to them, seemingly dramatic, and really make equality only for trace-free parts of them. Okay, so this will be our new Einstein equations, and they're rightfully called so Einstein equations because it was Einstein himself who introduced it 102 years ago. Okay, in a very nice paper written actually really beautifully. So the point is, if we write this new, so to say, Einstein equations, a traceless form of them, losing the trace part of these equations, nevertheless, if we assume that energy momentum tensor is conserved, and we assume as normal that there is Bianchi identity, so there is no torsion or some weird, strange, unusual connections, in that case, as a differential consequence of these two, if you want, constraints, it follows that the traces can differ only by a constant. And this constant is exactly your lambda. So you can basically reinstall it and put it back. So in that sense, lambda would be merely an integration constant, nothing else. But of course, if you have a dynamical system, when you have an integration constant, it implies that this is a dynamical degree of freedom, because to solve anything, you would need to know at least one data more. Okay. So these equations have also a nice property which makes it closer to normal mechanics, where we care only about differences in energy and not the origin of energy, in a sense that if we have vacuums, vacuum should be always Lorentz symmetric if you provide Lorentz symmetry. So basically all vacuum energy momentum tensors are lambda G mu. So this theory a priori is invariant with respect to such shifts. So this will be important. So basically we can shift energy momentum tensor by arbitrary vacuum contribution. So basically lambda G mu. And this theory is very well known under the name unimodular gravity. So there are hundreds and hundreds of works during this 102 years written on that subject. But it's a bit, in many cases, a bit confusing, I would say. At least for me, it was the case. And the literature is full of a bit contradicting statements. So the point is why it's called unimodular, that actually you can derive these traceless equations from normal Einstein-Hilbert action, just imposing the condition that somehow the determinant of the metric, or if you want square root of this determinant, is given by some function which is fixed, which you are not going to vary. So basically, the point is, of course, this is a choice of a partial gauge. So you can always do that, but not before you do the variation, right? And exactly the point that you try to impose this condition inside of the Einstein-Hilbert action gives you an additional degree of freedom, because formally speaking, it's not a legitimate operation. So usually in practice, people say that one can choose this function to be 1 for simplicity. And in that case, that's the origin of the name unimodular gravity. But we should keep in mind that the resulting equations are fully diffeomorphism invariant, and therefore there is no reason to impose this constraint which actually breaks this diffeomorphism invariance. So then in Noether and Tilboim, they were puzzled by the situation that we have nice generally covariant equations. However, we need to impose this ugly constraint condition, and they wanted to understand what are the real degrees of freedom of this beast. And what they have done, they basically promoted this useless function to be something dynamic. If you want, it's kind of Stuckelbergerish, okay? So, and they brought a very nice system, which is actually a theory of all de Sitter spaces and anti-de Sitter spaces, whatever you want. And this is a really simplest field theory one can ever write. Even though some people say that it's a super Young-Mills n equal 4, I think this is much simpler, because it has really just one global degree of freedom, and it's actually first order action. Your variables, not dynamical variables, but the variables which are going to vary in the action are the metric, the vector field W, and a field lambda. And basically it's very easy. If you vary with respect to W, then immediately you see that lambda is a constant. And then on equations of motion, this T mu is just lambda G mu. It's as simple as that. This is just really a theory of arbitrary lambdas, if you want, positive or negative. It has very nice properties. So namely, it has some gauge degeneracy on top of normal general covariance. So basically, you can add a vector which is divergentless. It has kind of fake violation of Lorentz symmetry because this vector can never be 0. But nevertheless, it's completely irrelevant because this value of this vector is not measurable by the gauge degeneracy. You can also think that this system is actually kind of making equality between two measures, the square root of minus g and this non-covariant divergence of the vector density. Another thing is that similarly to Ostrogradsky Hamiltonian, the system is actually linear in canonical momentum, even though I should admit it's not really like an Ostrogradsky structure. However, maybe tomorrow I will tell you how to get it from actually high derivative system. So you can think that this Lagrange multiplier, this lambda, comes into game from high derivatives. So the point is, so that's our canonical momentum. So the important thing is, despite of this Ostrogradsky, not really, but kind of, it's the same problem in the sense that it's linear. The equations of motion are such that this momentum you cannot exploit. You cannot really go to arbitrary negative values, because if you don't couple the system in some weird way, if you keep it as it is, you can choose your energy as low as you want, your Hamiltonian as low as you want at the beginning, then stays constant. There's no way to change it. Okay, then of course it's scale invariant because there is no scale in this section. There is no dimension for parameter. Okay, so now the point is what is more crucial for us, how to understand what is conjugated to what. So this is the key point that I will use later in going to G Newton and H bar. So we can recall the normal Hamiltonian form of the action of first order form, which depends on P and Q. Then we immediately compare with the action Newton and Planck wrote before. We see that the equation of motion for the special space-like part of the vector, so VI, is actually constrained. It doesn't have any time derivative, so it's a constraint. Then we can follow Faddeev-Jacquier. Faddeev-Jacquier tells us that we can plug in such constraints into the action, and then that implies that if we use this constraint into the action, we can move lambda pass through the integration over special coordinates in arbitrary foliation. And looking now at this structure and comparing it with the normal, basically Hamilton form of the action, we immediately see that what is canonically conjugated to lambda is this strange kind of charge. And this charge is not conserved. And this charge is actually a shift symmetric coordinate. So basically you can shift it by constant, and these global shifts in constant are generated by the original basically gauge symmetry. And what the meaning of this charge you can understand by just differentiating it in time, putting like normal boundary conditions that this vector Vi on the special infinities is vanishing fast enough. And then what you will see is that actually the meaning of this coordinate is that if you take it between two different Cauchy slices for different time slots, basically T1 and T2, the difference of this coordinate is actually 4 volume between these two Cauchy slices. Okay? So basically what we figure out is that the physical meaning of the quantity conjugated to lambda is 4 volume. Okay? And it's 4 volume between some fiducial Cauchy hypersurface that you can choose at the beginning and the Cauchy moment at the moment you want. So, but you know, it's unavoidable if you have quantities which are canonically conjugated by canonical quantization, especially here, so practically mechanics, they are going to be subject of normal canonical equations, canonical commutation relations, and in particular, directly Heisenberg uncertainty relation. Here it's much easier than for quantum fields. We don't need to smear, we don't need to do anything because it's mechanics. And then this Heisenberg uncertainty relation gives this very nice, very simple form, which you can write in the form of actually energy time uncertainty relation. So namely, if instead of lambda, you are going to talk about energy density by just dividing this lambda by G Newton, then you will see that basically the fluctuation of this 4 volume and fluctuation of this energy density in the cosmological constant are just related as energy time uncertainty relation. So it's larger or equal than h bar by 2. It's very, very funny because actually energy time uncertainty relation has very uncanonical meaning in normal quantum mechanics, but here it is just the result of your canonical quantization. So why it's interesting? Well, one could think that it's maybe not very interesting because if you take, let's say, collapsing radiation dominated and closed universe, then you would say, okay, the total 4 volume of this collapsing radiation dominated closed universe would be given by even by dimensions. You can take the maximum value of scale factor and it's basically power of 4. So of course, if the universe is big, it's a tiny quantity. Nevertheless, you could say that, okay, the fluctuation of this 4 volume should be, of course, less than the total 4 volume, because otherwise you are not in any way reasonable approximation to classical mechanics. So that implies that actually there is a limiting value. So you started classically from purely radiation-dominated universe, but in reality you have lambda there. And this lambda is not what you can rescale, you can basically do some renormalization or something like that. It's just there as a consequence of uncertainty relation, which you cannot kill, because otherwise you would kill all quantum fluctuations whatsoever. What is more interesting, so this is tiny, really, this lambda is tiny. What is more interesting is that this global degree of freedom provides actually global solution to a global problem, right? Because if you go very close to the end of time, when the universe collapses, the full volume between the moment of collapse and the moment where you are is shrinking, and it's shrinking very fast. And then one can check that actually if you're Planckish close to the end of time, you create enormous lambda. So in reality, I think it's kind of very similar to what Sakharov was thinking about that. Think about some medium, right? This kind of unimodular stuff provides you some medium, and this medium doesn't want to squeeze further than Planckish, if you want. So it wants to bounce back. So you generate huge cosmological constant, and it's of the same size as your radiation at the moment, like if you're Planckish away from the collapse. Interestingly enough, this dynamics does not depend what you write as high order terms, all these curvature corrections, they're completely irrelevant for that. Moreover, it's not clear how to use them, because usually you would need to kind of create negative energy, right? But here you don't do it, right? In the sense, okay, you maybe do it, but it's a global one. So it's not the one which you can exploit easily from, so there are no ghosts or anything like that. Okay, so basically there's some use in this construction. So, by the way, David, how much time do you have? You're muted, I think.
Sorry, you still have 10 minutes.
Oh, perfect. Okay, so now I finally can go to H bar in G Newton. So, but before that, I can tell you that, okay, instead of this vector field, what one can do, one can introduce connection of some Young-Mills field. And in that case, instead of W, you actually would use a Chern-Simons current. And that would generate you what we wrote with my students in basically February 2000. That would almost generate you the axionic cosmological constant. Okay, so why does it work? Because if you take this Chern-Simons current, then as you remember, the real variable in this W story, in an Otto-Teitelbaum story, was only the integral of CT. But this CT doesn't depend now on time derivatives of the gauge potential, so therefore it's a legitimate actually coordinate change. So basically you can really map it into this F of dual story, and now gauge transformations would create these shifts in this Chern-Simons current, because Chern-Simons current is not actually gauge invariant; it transforms inhomogeneously. Okay. So basically, in that case, one should also mention that there was this axionic, basically, the kind of set up by David Finkelstein, the guy who invented Finkelstein-Eddington coordinates, that actually he was speculating that maybe atomic physics and nuclear physics can provide you a fundamental volume element for basically this construction of unimodular gravity to explain the vacuum. And here you are. So basically, this F of dual gives you this volume element in some sense. You can also compare it with the Ariel-Zhitnitsky talk, which was here the first day, I think, or second day of the workshop. Okay, but now if you write this part of the action, then it's better to write it even closer to a kind of normal setup. So one can see that if you write this action, nothing changes, because even if I add potential, the only important thing for me was the variation with respect to the vector, and this gives me this theta is constant. So on equations of motion, theta will be constant. Therefore, this potential is just adding cosmological constant, and kinetic term is just irrelevant. It's just for fun. I could switch the sign, I could write whatever. So, and this theory is still not that good, but if we add here a normal kinetic term, then this would be normal axion. So basically, in order to kill it, what we need to assume is that the coupling constant in front of this normal kinetic term for this Young-Mills goes to infinity and somehow kills it. So that's a very naive version of confinement, but at least, you know, as a formal limit, one can do that. Okay. So basically now we can have also this, apply this construction now to G Newton, okay? And it's a second way to lose the trace. And as a side product, there is actually a way to make H bar as a global dynamical degree of freedom as well. So it will be actually 1 equal 1 instead of 0 equals 0. Okay, so what do? You write this equation normalized. Okay, so G mu divided by G, T mu divided by T. Trace is gone because if you take a trace, it's useless identity. 1 is equal 1 instead of 0 equals 0 in the unimodular case. And then if you apply the same thing, Bianchi identity, assume non-degeneracy of T mu and assume that T mu is conserved, you just get that this G and T, the traces are related by constant, you plug it in back, through la, you got G Newton merely as a integration constant. But again, integration constant means more data means more degrees of freedom. This time, this degree of freedom is again global. Okay, now another thing is that actually there are two ways of getting an action for that. And that's related to the point that this equation is scale invariant with respect to scales, rescalings of both T mu and G mu, right? And you can do them simultaneously if you want, or you can do them separately. But importantly, that it's invariant with respect to both scalings. And this provides two actually distinct ways of writing an action for that. Okay, just apply directly this construction. Just now, instead of this W, we write the divergence of the C. Alpha is again our field which we are going to vary. So it's really almost to not Teitelbaum. Instead of 1, we write R. And one can compare what actually Nemanja Kaloper, Tony Padilla, and George Zachariade, and I have forgotten the first name of Stefanician, what they were writing on kind of similar construction. Okay, so the point is that now we follow the same procedure which I explained for not Teitelbaum. There is no difference. So basically, the quantity conjugated to this alpha, or if you want to inverse Newton constant, is this integral. The meaning of this integral is nothing else as integrated Ricci scalar, or if you want, as a normal value of Einstein-Hilbert action without a constant. And then immediately we have uncertainty relation. Again, maybe this uncertainty relation is not very interesting because, of course, the 4 volume usually is huge, the fluctuations are small. So therefore, written in this way, the fluctuation of not G Newton, but L Planck, this will result in tiny, tiny deviations. But of course, if your 4 volume squeezes because your time to the singularity is very short to the end of time, then the whole thing becomes very relevant. Again, one can use the same procedure. Instead of nabla mu c mu, you write ff dual. The same logic applies. So the only thing what you have here is kind of non-minimally coupled to gravity axiom. But you would need to take again the formal limit to kill this f normal kinetic term for f. Okay, the interesting thing is that you can not only apply this construction just directly to the gravity part, which is kind of more or less straightforward, you can also apply it for matter part. Suppose you have your matter, let's say standard model. It's described by normal Lagrangian Lm. Now I write a different action. This different action will depend on metric, Lagrange multiplier, scalar field beta, and on a vector field lambda. As you see, I promoted this basically, I changed meta section a lot, right? So now that clearly corresponds to, so beta will be constant, right? So if I fix it initially, classically, that's just constant. Of the same reasons why lambda was constant, because if I vary with respect to L, this vector field L, that's what I will get. So that implies that actually the only thing I'm doing by creating this mass is just writing a non-standard momentum rescaling. So instead of, because real canonical momentum is now multiplied with beta. So basically, if you take canonical momentum defined for normal action with L, then now real canonical momentum multiplied with this constant. So this is just rescaling. So, but that rescales also uncertainty relations, or if you want commutation relations, doesn't matter. So the point is that you change effective Planck quanta, that's obvious, but because you have done it in the whole meta section, not in some parts, right? So it's everywhere. But of course, because now you take normal Einstein-Hilbert action and you wrote this part, you also change G Newton. So they're both rescaled. So finally enough, Planck length remains invariant. And then you can write uncertainty relation. Now it's uncertainty relation on this effective H bar, if you want barbaric H or H bar bar. And it's actually also kind of similar fluctuation, but now it's a fluctuation. You see what was interesting. So if the fluctuation of Planck length was related in the previous setup to the fluctuation of, if you want, Einstein-Hilbert action, here it's the fluctuation of normal meta action. Again, close to singularities that can be important. So now it's absolutely trivial how to make it frozen axionish. Just the same construction applies. The only thing you would need to universally couple this axion in front of the whole Lagrangian format. And finally, I'm now on my last slide. So the point is, people very often use a lot of like symmetry arguments why, for example, unimodular gravity should from the very beginning break diffeomorphism invariance and so on. So I like to work in arbitrary coordinates and especially in normal FRW coordinates and spherical coordinates and whatever I want. So not necessarily with the square root of g to be equal to 1. So therefore, it's better to use coordinates which we want. So now the action which you can see here, that's the standard action for unimodular gravity. As you see, it's not diffeomorphism invariant and it looks a bit bizarre, right? In reality, what happens is that you can take a not-Teitelbaum action, fix this W, and if you want, by doing that, you would need to work with your diffeomorphism invariance. So you would need to declare that there is a new time which is related to this WT component, and you also use the diffeomorphism invariant of the not-Teitelbaum action to kill other unnecessary components of this W. So the point is, what looked merely as a gauge choice, and it's actually very often confusingly discussed in unimodular literature because, oh, this is just merely a gauge choice. In reality, it's not, because even in order to write it, you already used one's diffeomorphism invariance. So therefore, you cannot use the same diffeomorphism invariance second time to impose the constraint that square root of minus g is 1. And it's very easy to see why, because if it was the case, then it would imply that the divergence of this vector W is 1. You cannot take a scalar quantity to be 1 by just changing your coordinates. Okay, so now what is funny, you can also write in the same funny manner unimatter gravity, or if you want unicurvature gravity, by just fixing the corresponding vector C and I haven't forgotten what was the L. You can also do it from the same reasons, because you have gauge symmetry, you have original diffeomorphism invariant set up. So you can just fix these things and get these two weird actions which are not generally covariant. So if you are really more precise, you can properly fine-tune the sign in front of, this minus can be changed to +1, and in the section for unicurvature it can be changed to -1, because actually in cosmology, at least in my signature conventions, this R is equal 3p minus epsilon, so it's better, most of the time in cosmology it would be kind of negative, the R. So therefore, it's better to make it minus there. I just choose it for simplicity, but you can make it plus or minus as you wish. And you see, formally speaking, both of these conditions are just, both these constraints, if you want, are just gauge conditions. One could think so, partial gauge conditions. That we show in our paper. It's very easy to show, actually. But actually, they yield dynamics from the same reason, because even in order even to write it, you need first to fix your variables by using diffeomorphisms. Okay, so, and we show, of course, that these two actions, they exactly recover the same dynamics, which we want. That's not that easy to show, but it is possible. Okay, so thanks a lot for your attention. I hope I'm not too much over time.
Just 4 minutes.
Oh, sorry.
So we have a few minutes for discussion.
It is due to uncertainty, David, of my volume.
So Sergey.
Hi, Alex.
Hey.
So, yeah, my question is about breaking of Lorentz invariance here. So I understand that at classical level, there is no breaking whatsoever. But when you go to, basically your results seem to break Lorentz invariance on the other hand. So you have these fluctuations of, say, lambda, which is constant in space, as far as I understand, but can fluctuate in time, yeah? Or you also have fluctuation of lambda in space. And yeah, if you don't, then my question is, at which point this like breaking into space and time happens?
Look, very, very, very good question. I also thought about it, and I was also puzzled about it. So the point is the following. So on one hand, this lambda is a true scalar canonically conjugated to for volume between hypersurfaces. So basically the point is, doesn't matter which hypersurfaces you choose. After that, you just count a gauge invariant quantity, a Lorentz invariant quantity, namely kind of what is between them. On the other hand, if you start doing universe, so basically, let's say closed universe, open, whatever, closed universe when it can be relevant, or maybe introducing boundary conditions, which is even more interesting. In that case, you definitely break Lorentz from the very beginning, right? Because you look how this volume changes with time, but not in space. So there are no fluctuations of this guy in space for sure, because it's a constraint. But
okay, yeah, so then it means that, yeah, kind of if I make measurement in space, like at two different points, I should measure the same lambda. But if I make different measurements like in different times, I will measure different lambda. So there is this asymmetry between space and time then, yeah?
Yes, but you would need to introduce from the very beginning kind of a different also pivot points, in the sense that you would introduce two different foliations.
Yeah, so basically you pick up foliation at some point, which breaks.
Right. The important thing is that this quantity corresponds really to differences. Conjugated quantity. It's not just one thing, because this one thing you can always change by this gauge transformation. You can always shift it. So really observable thing. So basically you would need to first say what was it before or what will be it in the future, actually, if you want, and then find the difference. Because you can even think that this lambda is conserved because it's momentum for the quantity which is shift symmetric.
Is conserved. No, but it has fluctuations, as you say.
Right, but it has, you see, it has fluctuations in the same way as momentum for a free particle has fluctuations.
Actually, can we change it? Can we change it? You know, with a measurement or with some operation? I mean, yeah, if it's dynamical degrees of freedom, we can affect it. So can we affect it?
Very good question. I don't know, because you see, this thing, formally speaking, is, I don't even know a more simple question. If you have event horizon, I don't even know how you would say what is the proper notion of an allowed fluctuation for this volume. In reality, you know, what I checked is that, for example, if you look at the collapsing radiation-dominated universe, and if you just say that you take whole full volume of the whole Cauchy hypersurface, in that case, this fluctuation of this lambda will be the same as fluctuation of the radiation, so as the radiation density, even on very, very short scales close to Planck, much shorter than T-Planck. But in reality, you cannot really say that, imagine you are kind of observer, you start seeing fluctuations which are larger than the volume which is inside of your event horizon. And classically, you do have event horizon because there is end of time. So basically, the amount of space you can observe is constantly shrinking to you. But if you use that as your fluctuation for this estimation, of course, I'm not doing proper quantization, and then you get normal Planck time. Because otherwise you will get super sub-Planckian times, and that's kind of similar to what some people doing as so-called S-brain. So basically, that would be kind of, because it's super sub-Planckian, it kind of reappears suddenly as almost delta function in time. But I don't know how to think about it. So basically, I think it's really important that you look at the volume inside of your event horizon at the moment.
I see. Okay, thank you.
Yeah, but I'm happy to talk about it.
Yeah.
So Sebastian, please.
Yeah, thanks a lot for the talk. So first, I wanted to make sure I understand correctly. So one way of formulating what you're doing, so for the cosmological constant, would be you start from unimodular gravity, and then you reformulate the unimodular gravity in the way following Hinot-Teitelbaum. And then these two formulations, like the standard unimodular gravity and the reformulation, they are the same classically, but then once you go to the quantum theory, they are different.
No, I don't think actually they are different, because in some sense, when you see, I think that's the key point, because if you start writing normal unimodular gravity, you fixed already one of your degrees of freedom in reality. So namely, by fixing this vector W, you fix the foliation, and then this foliation doesn't fluctuate anymore. So you see, it's in a sense, you start moving together with some quantity which already fluctuates. In that case, you don't see these fluctuations. That's true. But if you don't allow for that,
okay, so you're kind of saying because the cosmological constant is an integration constant, so it's part of the solution, then it will always fluctuate.
well, you see, it's from the point of view of normal canonical analysis, right? You cannot have one data, and just a sec, I need to switch off something because it will otherwise. Okay, so basically, your phase space should be even dimensional, right? Not odd dimensional. So therefore, there is something which is conjugated to this integration constant. And because you have an action, so there should be some Hamiltonian for that.
Okay. Yeah, I see the point. Maybe one very short other question. So you said that if you do the same for H bar, then the conjugate is the integral over the matter action. What happens in the limit of no matter?
Perfect, perfect. We also thought about it. We have a comment in the paper. Actually, it's a very funny situation. So somehow, if you write properly this nabla mu, whatever, with C mu there, then it's okay without matter. That's fine. So basically, you could have that at some moment this Lagrange multiplier, sorry, this Lagrangian density is 0. That's you can have that. But if you adjust, you cannot use the time anymore related to this vector. But you see, if you write it in this way, breaking diffs, so but by fixing it, in that case, that would be, of course, not correct. And the only way, in that case, to derive consistent things is to assume that this lambda m involves some cosmological constant. The same thing for R, by the way. So basically, if you start from a not Eitelborn, it doesn't matter whether R is 0 or not. If you write a not Eitelborn divergences. If you fix by diff invariance, if you want your time coordinates using particular ansatz in that case for this, what these vector fields are, in that case, you need to assume that after that, this R and L, that they are all non-zero. And actually, they should be even positive in some sense, because what you do, you use change of time. And then the moment when they change the time, basically you change the direction of time. So that's not an allowed procedure.
Okay, thank you.
So Luca, for a very short question and very short answers, please.
Yes, no. Actually, my question is very simple and short. Thanks for the talk. It was very intriguing. Actually, I really enjoyed. So yeah, my question is very simple. So I'm interested actually about this effective Planck constant that you define, which is quite unusual. I mean, we usually don't see like effect. We usually like see some dynamical coupling constant, but usually H bar is not a coupling constant, but you have some kind of effective H bar. So my question is, can this effective H bar go to 0 somehow?
Good question. Good question. You see, on one hand, I would tend to say no, because that would require for this beta to go actually to infinity. Let's sense some singularity, right?
Yeah, let's say because beta is a field, right? So I don't know if somehow in some regime this beta can be infinity.
Right, but you see, it's kind of funny because this beta doesn't have normal dynamics in the sense that you fix it by initial data. I mean, like classically, you fix it by initial data, it stays the same, right? But of course, if it fluctuates, then also infinite fluctuations of this beta would imply infinite fluctuations of this basically normal action. Oh, sorry, 0 fluctuation of the normal action. And actually, you cannot have it, right? Because normal action treated as an operator would still have fluctuations, right? Because it's a normal quantized system. So I think you cannot get beta to be infinity. By the way, I need to add that there was a different setup also studying how to make not that clearly how to make this H bar to be kind of dynamical variable. And I think it's Sean Carroll and Remen.
I see.
If you want, I can basically we cite them in the paper.
I can look at that then.
Right. But they use more complicated setup with some 3 forms. I don't know, some. It's kind of similar at them, but no, not the same.
So we should move on.
Okay, thank you.
Thanks, guys.
So thank you again, Alex.